Hello, this demo presents J2RM, a tool to process mappings from JSON data to RDF triples guided by an ontology structure. The mappings are defined as annotation properties associated with each ontology entity of interest, such as classes, object properties, data type properties, and so on. They are embedded in an ontology file, so that they can be readily deployed to automate RDF graph creation. Following, we will describe a general use case that presents the motivation for our work. Let's assume that an information architect wants to create an RDF graph based on data extracted from an information system. As often, it happens that the information architect will follow a simple approach to extract the required and curated data from the information system and expose them in an easy-to-process format, usually JSON. Why JSON? Well, the information architect knows very well that JSON has been used extensively in a variety of processing tasks as a serialization format, becoming the universal notation for data interchange on the web. As it happens frequently, the engineering team do not have a deep understanding of semantic web technologies and tools. The information architect would like to have a tool such that could abstract all the time-consuming complexities of creating and storing RDF triples on the fly from the JSON data. Moreover, the information architect would like to solely focus on designing the underlying mappings following the ontology structure. The main goal of J2RM is to automate RDF graph creation from JSON data following an ontology structure. As mentioned before, the mappings are defined as annotation properties and are embedded in an ontology file, so that can be easily deployed in different environments to automate the graph creation from a standardized JSON structure, tailored from the information system's data. This diagram describes the basic functionality of J2RM. The green box represents the J2RM processor, which is a software artifact capable of processing the J2RM mappings. These mappings encode the necessary rules that have the ability to selectively extract data and perform basic transformations and operations on the source JSON structure, while traversing the ontology model to generate the expected RDF triples. The processor has two types of inputs. The first input is the JSON dataset, which consists of multiple JSON documents. All of these JSON documents are expected to have the same underlying structure. As an aside note, all of these JSON documents, their structure, were designed from the original data source. The second input is the ontology definition file. The processor loads the ontology model and analyzes each ontology entity, classes, object properties, data type properties, annotation properties, and individuals in order to find the associated mappings to each entity. Internally, the processor keeps a dictionary of all the valid map values and objects from the JSON structure. With this, and while traversing the ontology model, the processor generates the expected RDF triples and stores them into the target triple store. Following, we will present an example that shows how J2RM works. First, we will present the structure of a JSON document, and we will highlight the relevant features that we will consider for this use case. Then we will present the ontology model and its definition file, along with the J2RM mappings. In this part, we will highlight some of the basic features that we have implemented in J2RM. Afterwards, we will run the processor for these two inputs, and we will present the generated RDF triples. This is the example JSON document. The data comes from a medical research grants information system. So there was a previous process that extracted the data from this information system and built this JSON document. As you can see, this is a quite large document. So this document has three high-level JSON objects: general metadata, specific metadata, and associated metadata. In our case, we will only focus on the information related to the associated metadata JSON object. So this object has the following structure. All of these attributes are related to one concept. This concept is about the application of a grant. Then we have the information related to the grant itself, which we deem as public information, whereas this information of the application is private. Now, this distinction is useful because we would like to generate some triples in the so-called private triple store. So all of these triples, for example, we would like to be in the private triple store, whereas all of these triples we would like to be in the public triple store. So this information stored here in this JSON array is related to the grant, and then we have this information under the team data JSON object. This information is part of the application, and basically the structure is an array of JSON objects. Each JSON object has information related to researchers, and then each JSON object has an array of various JSON objects. All of them are related to the information of this researcher. So these JSON objects, they describe information related to each researcher. They are regarding codes of research related to each researcher. So as you can see, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8 researchers related to the application. So one thing to notice in here is the complexity of the JSON structure. And among these, of course, based on the ontology model, we would like to create triples and extract the information from this JSON structure. So coming back again to the application information, you can see in here that we have information regarding, well, this is the identifier. Then we have attributes that they are treated as integer, even though they were not generated as such. One interesting thing here to see is that we have a field with the name keywords, and then each one of these follow this structure. So in this case, it would be really interesting and useful if we would have a mechanism to automatically split this value and generate a triple for each of the keywords. So in general, as you can see, we have the structure is complex. So we have a JSON object that has arrays, that has objects that have arrays. So we have nested arrays with nested objects. That's the natural structure of a JSON document. So we are interested to define the mappings and how to access each part of the data. And based on the ontology definition, we will generate the respective expected triples. One thing to notice, for example, is that in order to identify some of these instances in the RDF graph, we keep track, well, the processor keeps track of the structure, so we have here nested codes in order to build the identifiers. So the same goes like from the application towards each of these JSON objects of the team data. This diagram represents the ontology model used for this example. The ontology, it's about research grants and their applications. Main classes of this ontology are grant application, grant, investigator, and research institution. You can see in here that grant application has multiple attributes and also connects to other classes. The class investigator abstracts, encapsulates the information related to each investigator. So as part of the information also we have the, for some investigators, the ORCID, which is modeled as an instance of this class. The connection between grant application and investigator is through a role of researchers. There is a property called has researcher that defines multiple sub-properties. They are named as presented in here, has researcher 1, 2, 3, up to 10. So the information from the related to the grant class has many attributes and some connections to other classes. From this JSON array. So all of this information is modeled into that class grant. Last, all of these black boxes that you can see here in the model identify the triples that will be generated in the so-called private triple store, whereas information like the one related to the grant class will be generated in the public triple store. We have opened the ontology definition file in Protege. We will review how we associate for each entity in the ontology the defined mappings. So as mentioned before, each ontology entity will have via annotation properties the corresponding mappings to the JSON structure. Along with each mapping, one can specify the target endpoint and the target graph where the triples will be created. This annotation property defines the target endpoint, which is a label that identifies the Sparkle endpoint access where the triples will be created for this mapping related to this ontology entity. These labels are defined in the configuration file of the J2RM processor. The other type of property that can specify is the target graph, which is the name graph where the triples will be created. In this case, the name graph is defined as a namespace prefix in the ontology file. So for this example, we have this namespace prefix, which is defined here in the ontology file. So we take this IRI as the identifier of the target graph where the triples, in this case, for this mapping related to this entity, will be created. The way how these mappings are processed depends on the nature of the entity. So the processing model for classes, it's different than the way how they are processed for object properties or data type properties, and also for annotation properties. The mappings related to classes generate this kind of structure for each triple. The mappings related to object properties generate these type of triples. And the ones for data type and annotation properties, they generate this type of triples. Following, we will describe how each of these mappings work. Before we explain how the mappings work for this example, we are going to briefly introduce the formal grammar of the J2RM mappings. The J2RM mappings are being designed as an extension of the JSON pointer specification. These extensions define some basic transformations and operations applied to the JSON data. Some transformations in here are represented by these meta characters that we will present later. And some operations include the conditional paths, or also equal values, that is, if the map values matches to another path, to the values of another path, and relational evaluation of the map values. There are two types of mappings based on their processing model. The ones that start with a slash are processed directly as JSON pointers, whereas the ones that do not start with slash are processed internally, and the processor keeps track of all the map JSON objects and values based on this mechanism. Last, this constructor, ABL resolution, is useful to disambiguate the entity name of the class of domain and range when the context cannot know to which class it will generate the triples. Frequently, we have this situation in the processing of object properties and also data type properties. Following, we will describe how the class mappings work. The class mappings create an instance for each map value with this structure. So basically, J2RM generates an RDF type triple for each map value, creating an instance associated to the specific class for each mapping. So in this case, we have a JSON pointer that maps to this value. This value is used to identify the instance associated to this class. This is because this mapping is being used or associated with this class. So the resultant triple has as a subject this URI. J2RM uses the class name and the map value to identify the instance for each class. The same situation goes to the instances of grad application. We have the same kind of mapping. Therefore, the resultant triple is this one, or has as a subject this URI. Another type of mapping is shown in here, the one associated to the ORCID class. Now, as you can see in this case, the path is not a JSON pointer, however, is processed internally, and it keeps track of the map objects and values, and this path points to this array of values. So these are the array of values of this type of mapping. So you can see in here that we have multiple orchids, and some of these values actually they are empty. Empty values are skipped, and of course only the ones who have a value are the ones that the processor takes to generate the triples. So in this case, the mapping yields to an array of 1, 2, 3, 4, 5, 6, 7, 8 values. However, only 2 of them, these 2, will be used to generate the instances. In this case, the meta character hash indicates that the map value is used as is. That is to generate directly an IRI. Some specific validations are used to validate to see if this value is a valid IRI. However, the main idea is that the hash character indicates that we will use directly this value as an IRI for the identifier of the instance. So in this case, for the class ORCID, we have these 2 instances, or these 2 valid values. And for this case, the resultant triples are these ones. So as you can see, we use that value directly as an IRI for the instances. Another type of mapping is shown in here for this class. So in this case, this path points to this value. This value in here. Now, as you can see, this is a simple string value with blank spaces. In this case, the meta character exclamation mark indicates that the value is used to generate an IRI. So the string value will be transformed and make it usable as an IRI. Therefore, this value will be used to generate this IRI, as shown in here. So this will be the IRI of the instance generated using the exclamation mark meta character. Last, another type of class mapping is shown in here. This is an example of a multi-pointer mapping. A multi-pointer mapping has the capability of define multiple subpaths of a common shared ancestor path. So in this case, we have that application ID and team data / individual ID, both of them are subpaths that share as the common ancestor the associated metadata path. This type of multi-pointer mapping is useful when we need a composite ID. That is, we need to form an ID based on multiple values mapped to different parts of the document that they share a common ancestor. So for this case, the composite value or ID will start first using the application ID, followed by the individual ID for each map in this JSON array. Therefore, for the JSON document for this example, we have here the application ID. So this is the first map value. And then we have this JSON array of these team data / individual ID values. So at the end, this will result into all of these values, generated values. And each one of them will be used to create an instance of this class. With these values, J2RM is capable to generate all of these URIs that identify various instances related to this class. Following, we will present how the mappings work for data type properties and annotation properties. So this type of mappings create a triple for each map value with this kind of structure. J2RM analyzes the ontology, and for each class and subclasses of the class hierarchy that has this property as a class restriction or part of its domain, it will create a triple for each mapped instance. So J2RM keeps track of the instances generated in the class mappings, and based on the mappings associated to data type properties or annotation properties, it will generate a corresponding value to complete the triple. One example is this kind of mapping. As you can see, this mapping is associated to the full name data type property, which we can see in here that is part of the class restrictions of the investigator class. Here we have full name. So J2RM keeps track of all the instances that have been mapped to that class, investigator, and then it will use this path in here and the map values of this path to generate the RDF triples for this data type property. So this path will map to an array of these values. And here we have associated metadata / team data / full name. So we have all of these values from this JSON array, which they will be used for each instance already mapped from the class investigator. In this case, J2RM uses the context of the map JSON objects from the instances to identify the subjects and the values for the data type properties to be generated. So if we check the ontology, we will see that this data type property maps to full name, which is an attribute, field of team data. So for the class investigator that has this class restriction of full name, we see that the instances are mapped to team data / individual ID. Hence, the context of the map JSON objects, they are in the same JSON object, each of these fields, individual ID and full name. So for each one of these instances, it will generate this corresponding RDF triple. Therefore, the generated values are shown in here. As you can see, for each investigator, we will have its full name and its value. And we have all these triples being generated. Therefore, the generated triples are these ones. So we see in here the URI of the instance and the associated value for this data type property. One important thing to notice in this mapping is the usage of the meta character tilde. This meta character indicates that the map value is used to automatically create an RDFS label triple along with this data type property. So in this case, the same result will be used to generate an RDFS label triple using the subject part and the map value in the object part of the triple. Of course, this is useful to automatically generate this type of labels throughout the knowledge graph. Hence, we also generate these triples shown here. As you can see, the RDFS label associated generated for each data type property of the mappings. The same time of usage of this meta character tilde can be seen in this other example for this annotation property, DC title. So these two mappings, we generate the triple DC title mapped to this value, title clean, and this other value for these specific classes. And the meta character tilde also automatically generates an RDFS label for these two map values. Thus, we will have an RDFS label with the value of title for the grant application instance and also another similar for the grant instance. So the map values will be, the resultant RDF triples will be like this. We have here the grant application instance, this is title, and this is the value, the map value, and also its RDFS label. Another interesting and useful kind of mappings is shown for this data type property keyword. This mapping creates a triple for each value found when splitting the map values using this delimiter. So in this case, we are using a blank space, the pipe character, and another blank space as the delimiter. And thus, it will generate various keywords based on this map value. So this path maps to this value. And as you can see in here, we have several, this string value has this delimiter, and therefore this will yield to a different type of keywords. So the resultant part is that for each split value, we will have a triple with the data type property keyword. So we will have this result. Therefore, we will have these triples generated. Another very useful type of mappings is the usage of conditional paths. Conditional paths work in this way. So J2RM will map to these values only if the conditional expression in here will evaluate to true. So in this case, we have here an AND expression, and therefore we have two conditions, two paths to evaluate. So if this path in here evaluates to true and this path in here evaluates to true, then it will generate this, or it will map to these values. Let's take a close look in our JSON document, in our example JSON document. So as you can see in here, the first part of the condition, associated metadata / scheme, maps to this value, program grant, which is true. The second part of the expression, associated metadata / application year, map to this value, which is less than 2019, so also is true. And therefore, our expression evaluates to true. Therefore, it will map correspondingly to this value, and therefore we will retrieve this value. Hence, this mapping will evaluate to this, it will generate this triple. So we have for this instance, this is the data type property and the corresponding map value. As mentioned before, this instance is kept in memory in a registry. So J2RM processor knows that for this class, we have this kind of mapping, the generated instances, and as a class restriction, it has this data type property. So this one is used as the context JSON object to process this path, this mapping. This will result in generating this triple, which is the one that we wanted to. Last, we will present this other type of mapping, the one that we have here for this data type property. So in this case, this meta character defines a mapping to a common JSON object ancestor. So how this triple is generated? Let's see first the subject part of the triple. In this case, the link data type property is part of the class restriction, is a class, part of a class restriction of the grant class. You can see in here that we have here link as a class restriction of grant. Therefore, the processor knows that the instances of grant will be used as the subject part of the triple. Now, the subject part of the triple, here is the mapping. So we have associated metadata slash grant data slash ID. So in this case, it maps to this value. We have here associated metadata and grant data slash ID. So it maps to this value. And now let's take a look of the object part of the triple. So in this case, the object part, the mappings are pointing to this value. So it's a value that is under the path grant data slash links slash href. So in our JSON document, we see that this value is in here, slash grant data slash links slash href, and this is the map value. So because J2RM processor keeps the context of the map JSON object, in this case, we see that this structure maps to a descendant object of the object where the ID lies. So therefore, we use this meta character to find the mapping to a common JSON object ancestor. So in this case, the common JSON object ancestor goes to this part, grant data. Because grant data has ID and has links. So this meta character is useful to state the mappings is in one of a JSON object ancestor. And with this kind of mapping, the resultant triple is this one. So we have here the subject part for this data type property link and the object part. And with this, we generate this triple in here. So we have here the subject part and the desired object part. And we generated as this type, any URI, as defined in the ontology file. Last, we will present how the object property mappings work. These mappings create triples Let's take a look at simple cases. Has FOR object property is defined as a class restriction for two classes. For the grant application, we have here has FOR, and for this class, FOR category, we have also has FOR. So for grant application, we can see that the map values for the instances are based on this path. So this is a JSON pointer slash associated metadata slash application ID that points to this value on the JSON document. And then the range of this object property is this class, FOR. In this case, FOR has two paths that define the mappings for their instances. So the first one is associated metadata slash field of research code, and this other path. So following this path slash associated metadata for this class grant application, J2RM tries to find the connection between the instances from the domain part to the range part. So in this case, the instances for the domain part are located into this JSON object, in this JSON object. And the instances of the range part are located in two parts. One is this JSON object. So in this case, is the same JSON object associated metadata and points to this field. And then the other part points to a JSON array of these values in here. However, the path defined as the connection between the domain and the range part, it just refers, is a JSON pointer that refers to associated metadata to this JSON object. Therefore, the resultant generated triple, in this case, goes from this instance of grant application, has this object property, has FOR, to this instance of the FOR class. And therefore, we have this triple being generated. One thing to notice in here is the usage of the meta character at. This is used in several mappings, and this character indicates the entity, that is the domain class in this case, attached to the path. And this is useful for entity disambiguation. Like in this case, we have multiple paths, and this object property is used in this case in two classes, grant application and FOR category. So in order to know exactly which path to apply for each case and for each class, we use this meta character to make this disambiguation. So we can see in here that for this case, we are using a JSON pointer processing model. In this other example, for the object property has ORCID, we are using a different type, the other type of processing model. So this object property is defined as a class restriction of the investigator class. So here we have has ORCID. So this will be the domain. So this is the mapping that identifies the instances of the domain part, and the range will be this class. So we know that this will be the instances of the range part. So in this case, this path associated metadata / team data maps to the following values. So we map in here to these values, actually to the JSON array pointed from this path. So we have associated metadata / team data. So the result is all of this JSON array, and for each object of this array, we have this structure. So as we see before, the domain part of the object property that we are analyzing points to the individual ID, which identifies the instances of the investigator class, and the ORCID field, which identifies the instances of the ORCID class, that in this case is the range part of the object properties that we will generate. So as you can see, both mappings for each element of the JSON array, for each object, we know the context. So the J2RM processor knows how to generate for each subject, connects to each object, following the processing of for this object property. However, as mentioned before, all the empty values are ignored, and only the values that have been successfully mapped to instances are the ones that the processor generates for the final triples. So in this case, we generate these two triples. So for this instance of investigator has ORCID, this instance of the class ORCID, and so on. And thus, the resultant triples are in here. So we have the domain part, object property, and the range part. So just to highlight this important mechanism, internally, the tool keeps track of the context for each map JSON object. That could result in a valid connection. Another type of mapping is shown in here. This type of mappings defines two different paths, one specific for the domain part, one and another one specific for the range part. These mappings are defined as an OP map, as shown in here in the formal grammar. These type of mappings are useful to indicate explicitly that the connection between the domain instances and the range instances are not based on a contextual JSON object, map JSON objects. In this case, for the domain part, if it's in blank, then this indicates the usage of the already known instances from the domain classes. And for the range part, indicates the mapping to the values that are equal to the member role values, map values that are equal to this constant, CIA. So in order to analyze this kind of mappings, the processor takes a look of the definition for this object type property, for this object property. In this case, it looks that it is a subproperty of this one. So here, it knows what is the range, for this case is researcher, and then it looks the classes that have defined this object property as a class restriction. So the object property has researcher is defined as a class restriction of this class, grant application. Therefore, the processor knows which instances will be used as the subject part. In this case, it's just one single instance is the ID for the grant application. Then the processor takes a look about the range. In this case is researcher. So for the researcher class, it takes a look of this class and its class hierarchy, looking for valid maps that will be used to generate the object part of these triples. So in this case, there are no mappings for researcher, there are no mappings for partner investigator, but there are some mappings, or there is a mapping for chief investigator. And this is a multi-pointer, a composite mapping. So then the processor will know the instances to use for the object part. And it will use this definition and will only look for those instances that have this, that comply to this restriction. So looking back again, the subject part is grant application. So this is a JSON pointer, points to application ID. So it points to this instance. Then the object part points to researcher, which at the end will use this mapping, and as we can see, points to the composite values of this JSON array. So it goes to team data individual ID. So here in the JSON document, we have here the team data, and the individual team data individual ID. So for each one of these objects will be possible instances that the processor will use to generate the object part for these triples. Now, it will take a look about how to connect these two paths. So in this case, it will apply this restriction. So only for those ones that have this field member row with the constant value of CIA. So in this case, only this object will be evaluated to true. So therefore, only this object will be used to generate the triple. Therefore, the resultant triple will be this one. So we have here the subject part, application ID, has researcher 1, which is the object property that is being analyzed, and points to this instance. In this case, the instance who has this CIA constant value. Thus, the tool will generate this triple. So we have here the subject part, the object property, and the object part of the triple. Last, for this property, we can illustrate two mappings. The first one, we explicitly disambiguate the domain and range classes that the processor will use to generate the triple. So in this case, as you can see, there are multiple classes for the range, and also this object property is used as a class restriction in multiple classes. So this constructor here, following the formal grammar, the OWL resolution constructor, is used to explicitly state that in this case, this is the entity that represents the domain class, and this is the entity that represents the range class, to generate these mappings. The second mapping uses this operator, the equal values operator, to indicate that the processor will map to these values of the left side of the operator, will map to these values in here, only if those values are equal to the values of this path. So let's take a close look to this object property. This object property is defined as a class restriction of this class. And then you can see it maps, the instances maps to this value in here. So, as mentioned before, the meta character exclamation mark is used to take the string value and generate a corresponding ID used for the URI for this instance. Then the range part of the object property applies for the classes identified here. So for FOR, actually the maps goes to another part of the JSON document, so you won't be able to find any matches. However, for the research institution, the map goes to this part, associated metadata, team data, primary institution. It maps this part of the operator. So it will try to find the values of this JSON array that correspond or matches to the same map values of this path. So in this case, the JSON array here, associated metadata / team data, then / primary institution, for all of these map values, it will try to find those that have an equal value or match with this one in associated metadata / unscanned data / managing institution. So in this case, it will only match to these values in here. And therefore, it will generate this triple. The identifier of this class for this instance, then the connection and the object property about to the instance for this class. Hence, we will have this triple as the result. We have presented the mappings that currently J2RM supports. The object property mappings create triples between sets of map values for each identified class that is applicable in the analyzed context, that is, class hierarchies, subproperties, and so on. The structure generated is as follows. The domain data ID corresponds to the map instances of each object property domain class, and range data ID corresponds to the map instances of each object property range class. So the mappings are paths that define the connection between the domain data ID and the range data ID. Following, we will run the J2RM tool for the example explained in this demo. The J2RM tool has a configuration file where one can define general parameters, as for example, the Sparkle endpoints access and some parameters related to the ontologies to be processed, such as the default name graph. So in this case, we will generate the triples for this document. So starting here the process, we can see here the output. The main model generates triple for each type of ontology entity, for classes, individual, object properties, data type properties, and annotation properties. So as you can see in here, all the triples have been generated, are being generated. And the process has finished. So we can take a look of the triples that have been generated for this example, when we're running for this example. So first starts with generating the identifiers for the instances for each class. Then goes for the individuals. In this case, we don't have any individuals defined in the ontology. Then goes for the object properties, and it generates here the triples for each mapping for the object properties. You can see in here connections between the single instances and composite identifiers. And then it goes to generate the data type properties. So of course, it checks the XSD data type and so on. Here are all the values. This is the case for the keywords, generated keywords. And last, it generates the annotation properties. In this case, we only have two DC title properties. One related to the grant application instance, the other related to the grant instance, and its corresponding RDFS label. And now we will check the two Sparkle endpoints to see the triples that we have created. So In this case, this is the Sparkle endpoint for the so-called private triples that we have been created. So if we count the number of triples, there has been this number of triples created. Then, if we go to the next Sparkle endpoint, this is the so-called public Sparkle endpoint. And we see in here the number of triples created. So if we try to check for all the triples, so you can see in here, these are all the triples that have been created in this Sparkle endpoint based on the automation of how to access the underlying JSON structure from the example explained. And then if we go to the other Sparkle endpoint, we can see in here basically a subset of this graph, of this private graph. So here we have some of the triples, but the ones that are deemed as public and therefore created in this Sparkle endpoint. So this concludes the demo for J2RM. Hopefully it has been quite detailed in order to explain the current functionality of this tool. We appreciate your attention, and hopefully you will find useful this tool for various use cases where we can automate the RDF graph creation directly based from JSON objects, JSON documents where the mappings are guided by the ontology structure. Thank you very much. In here, we are running the J2RM mappings triple creation process for a dataset that consists of thousands of JSON documents. As you can see, for each document, the J2RM processor traverses the ontology definitions, gets the corresponding mappings, and it creates the triple, the required triples based on the rules. So far, the process has been run for 55 documents, and in here, it's creating the data, the object properties, and now the data type properties. And right now, it's starting with the document 56. So with this, we can automate the creation of any type of RDF graph guided by the ontology definitions from data stored in JSON format.